All right, so today we're talking about percent composition, empirical formulas, and molecular formulas. This all requires use of the mole concept, right? So we're going to be building on things we've talked about already. If you don't already have a periodic table handy, you might want to pull one out. Of course, you're all sitting close enough you can see the one on the wall too. So let's talk about percent composition. The percent composition is the mass of the element in the compound, and I'll show you an example of what that means, divided by the molar mass of the compound. So how do you get the mass of the element in the compound? That would be the molar mass of the element times however many of it you have. And that sounds kind of complicated. Let me explain. If you're doing water, H2O, right? And you wanted to know the percent hydrogen. If we're doing percent hydrogen in water, that would be molar mass of hydrogen times 2, right, because it's H2O, divided by the total molar mass, so 18.01. Okay, so you just take the mass of the elements in that compound, divided by the total molar mass, then multiply by 100. So it's a lot of words to explain something that's really not that difficult. And all of your percent compositions should add up to 100, right? If you're doing water, H2O, the percent hydrogen plus the percent oxygen should add up to 100, right? So you can always check your work that way. If you get 99.999999999, right, that's just rounding. Okay, and if you get 100.00001, that's also just rounding. So let's look at an example. What percent of ethane is carbon? Okay, so there's the formula for ethane, C2H6. And I want to know what percent of this is carbon. So this is the mass of carbon in ethane, right? It's 2 times the molar mass of carbon. Why am I multiplying by 2? Because there are 2 carbons in ethane. Does everyone see where that 2 comes from? And then 12.011 is the molar mass from the periodic table. Excuse me. Wow. I'm choking on my breathing. How did I get this bottom number, the 30.07? Where'd that come from? What is that? That's just the molar mass, right? So it's the mass of carbon in that compound, so 2 times the molar mass of carbon, divided by the total molar mass times 100. So that'll be 80. Now, if I wanted to know hydrogen as well, I could calculate it, right? I could say 6 times 1.008 divided by 30.07. Or I could say 100 minus 80, right? Because these 2 values should add up to 100. Does everyone understand how these numbers came to exist? We good on how to do this?
Wait, didn't you say it has to add to 100?
If I asked for hydrogen, hydrogen plus carbon should add up to 100.
Okay, but you just like that.
Right now, I just asked for carbon. Yeah. But if I'd asked for hydrogen too, you could just subtract since there are only 2 of them.
Okay.
Does that make sense? Okay, you do this one. Calculate the percent nitrogen in calcium nitrate. Pause the recording while you think about that one. All right, let's go over this one. So the first thing you need is the formula for calcium nitrate, right? Calcium nitrate's formula CaNO3 2. So there's the molar mass of calcium nitrate. I came up with 164.1. I did some rounding. So the mass of nitrogen in calcium nitrate would be 2, right? Because you've got to distribute that 2. So 2 times the mass of nitrogen divided by the total molar mass. So I got 17.1%. Did you? Do we agree? Any questions on how to do percent composition? Any questions on how this works? All right, do another one. I want to know both hydrogen and oxygen this time for hydrogen peroxide. So figure out percent hydrogen, percent oxygen. Of course, you need to know the formula for hydrogen peroxide is first. I'll pause the recording. All right, let's go over this one. So you need to know the formula for hydrogen peroxide. What's the formula for hydrogen peroxide? H2O2, right. So if you calculate percent hydrogen, you could calculate percent oxygen the same way, right? Or what's the other way you could get percent oxygen? Just subtract from 100, right? Either way, you're going to get the same proportions. Now, in terms of decimal places, we're not going to be too obsessive about sig figs here, right? Because we're not using any measured values. So you can carry yours out to 2 decimal places. That's fine. Do we agree? Did you get it right? If you made a mistake, you see where you made it. Any questions on this one before we go further? Okay, now when we're doing percent composition for a hydrate, remember a hydrate is a compound that contains water as part of its formula, right? So this is copper 2 sulfate pentahydrate. Remember we talked about hydrates when we did ionic bonding. So this is just part of the molar mass, right? So if I'm calculating the molar mass of this thing, it would be mass of copper plus mass of sulfur plus 4 times the mass of oxygen plus distribute this 5. 10 times the mass of hydrogen plus 5 times the mass of oxygen, okay? This is considered part of the formula, so its molar mass needs to include that water as well, okay? And don't forget, you need to distribute that 5. So for instance, if I said, okay, what percent of this compound is water? What would I do there? This is the total molar mass, right? So there's the total molar mass. When I distribute all my coefficients, I get 249.62. So the mass of water would be, right, we're just doing this part right here. 10 times 1.008 plus 1 times, 5 times 16. I'm doing some pretty significant rounding there. So then when I take my percent water, that's just the mass of the water over the total molar mass, so 90 over 249 divided by times 100 gives me 36%. Do you see how we did it with a hydrate? Do you see how it works for a hydrate? What if I said, what's the percent copper instead of percent water? If I say, what's the percent copper? You just take the molar mass of copper divided by this whole thing. If I say, what's the percent sulfur? You'd say, okay, there's 1 sulfur, so mass of sulfur divided by total molar mass. Okay, so it works just the same for if you're looking at percent water or percent single element. Does this make sense? Yes, yes, yes. Okay, what about this one? Let's pretend you're going to do an experiment similar to this. If your experimental percent water in copper 2 sulfate was 32%, what is your percent error? So that's what the value should be, right? So that's the actual value. Here's your experimental value. Does anyone remember the formula for percent error? It's not actual over theoretical, that's percent yield. Does anyone remember the formula for percent error? We've done it in lab a few times.
Actual minus theoretical over.
Right, right. So it's actual minus your experimental value over your actual value, right? So the experimental value is the value you get. This is the value you expect it to be. So 3.2 minus 3.6 divided by 3.6. Negative 11. How come it comes out to be negative? Well, because it should be 36. You got 32, so your value's too low. Right? So if you ever get a negative percent error, that's okay. That's just telling you that your value's too low. So you've done this in lab a few times too. Okay, why don't you try this one? And while you're at it, why don't you name it for practice? ZnCl2.4H2O. I won't tell you Anything other than that? What percent's water? Let me pause the recording. Okay, let's go over this one. Now, what is the name of ZnCl2.4H2O? What's the name of the ZnCl2 part? Zinc 2 chloride, right? And what is the prefix that goes along with 4? Tetra. So it'd be zinc 2 chloride tetra hydrate. Good. All right, so we want to know what percent of this hydrate is water. So we need to figure out the mass of the water, so the mass of 4 H2Os, divided by the total molar mass of this thing. So I came up with 34.6%. Do we agree? I got 208.346 is my total molar mass, and the mass of water I got 72.056. Do we agree? Yes, yes, yes. Any questions on this problem? If you made a mistake, you see where you made it. Okay, now we're going to talk about, for the rest of today, empirical and molecular formulas. Okay, these are two different types of formulas. They're really different, okay, so we need to make sure we understand how they differ from each other. An empirical formula is the formula with the lowest ratio of elements. Okay, so for instance, think about it like when you were in 5th grade and you were reducing fractions, right? 5/10 reduces to 1/2, right? So the empirical formula is like the reduced fraction. Okay, if you think back to elementary school and you reduced fractions, right? The empirical formula would be the reduced fraction. A molecular formula is an empirical formula that's multiplied by some factor. In other words, a molecular formula can be reduced. An empirical formula cannot be reduced. Molecular formula can be reduced. Empirical formula cannot be reduced. So here's an example, right? CH versus C6H6. Okay, a lot of times the empirical formula is a substance that doesn't exist. There's no such compound as CH. It doesn't exist. But that is the empirical formula of this compound, which is called benzene, and it does exist. Okay? So many times your molecular formula, your empirical formula is something that doesn't really exist. Now, a lot of times your empirical formula is something that exists. It just depends. Okay? But the molecular formula is the empirical formula multiplied by some factor. So if I multiply all of these by 6, because that's 1, right? 6 times 1 gives me 6. 6 times 1 gives me 6. This is molecular. This is empirical. Does everybody see the difference between an empirical formula and a molecular formula? The molecular formula would be like the unreduced fraction, right? 4/8. Whereas the empirical formula would be 1/2, right? Another thing that's interesting about empirical formulas is that several molecular formulas can all have the same empirical formula. Right? So this could be the empirical formula for a lot of different things. So there could be several molecules that have the same empirical formula. Questions about empirical versus molecular formulas? Can everybody understand the difference conceptually? So we're going to calculate both today. Okay, let's go through these together. You decide, is it an empirical formula or is it a molecular formula? Is this formula empirical or molecular? Molecular, right? Because the empirical formula would be CH2O, right? 6 divided by 1, 6 by 6, 6 by 6 divided by 6 gives you CH2O. Okay, is this an empirical or a molecular formula? Does the ratio 5 to 5 to 5 reduce? Yes, if you divide everybody by 5, right, you get CHN. So that would be a molecular formula. What about N2O? Is that empirical or molecular? Empirical, right. The ratio 2 to 1 doesn't reduce any further. Do we understand the difference between an empirical formula and a molecular formula? How to diagnose that? Okay, so here are some examples. Look, both of these have the same empirical formula, By the way, CH, that's a substance that doesn't exist. There's no such thing as CH. But both of these compounds have the same empirical formula. Right? So C2H2 and C6H6 both reduce to CH. There's no such thing as CH. But there is C2H2, there is C6H6. This one's benzene. And this is a carbon-carbon triple bond right there. Questions about empirical versus molecular formulas? We good? Okay. Here's another example. These are all compounds that have the same empirical formula. These are all CH2O. Oh, my slide got all funky. Right, that E should be right here. So formaldehyde, acetic acid, lactic acid, erythrose, ribose, and glucose. I couldn't read my own slide. It's got funky somehow. Right, but all of these have the same empirical formula. Right? And how do you get from the empirical formula to the molecular formula? This is the factor we're multiplying by. Right? If we multiply CH2O by 1, we get this. If you multiply CH2O times 2, you get this. If you multiply by 3, you get this. By 4, you get this. By 5, you get this. By 6, you get this. Okay? So do you understand the difference between an empirical and a molecular formula? So we're going to calculate an empirical formula first. Then we're going to figure out what this multiple is. Then we're going to multiply by that factor. And then we'll turn our empirical formula into a molecular formula. So that's where we're going for the rest of today. Is everybody with me? Everybody good? Okay. So we're going to use experimental data for calculating empirical formulas. So these data would have to be given to you. And we're going to be using data to do this. So we can all pretend that we're forensic chemists. We're trying to identify a mystery powder. We do our elemental analysis. We get a bunch of percents. Now let's figure out what the identity is. So here's how you're going to do it. These are the steps. We're going to pretend that we've got 100 grams of the substance, because that just makes our math easier. Okay, because if it's 56% nitrogen and 12% oxygen, right? If it's a 100-gram sample, then that means you have 56 and 12 grams. So we're going to assume we have a 100-gram sample. So that means we can take all of our percentages that I'm going to give you and just substitute percent for grams. And that way we can convert grams to moles. Everybody gets converted to moles, okay? Then you're going to look at those number of moles values. You're going to pick the smallest number of moles. Okay, you're going to pick the smallest number of moles. And you're going to divide everybody by that smallest number. This will give you your subscripts. Okay? Now here's something that you need to be aware of. When you divide through by the lowest number, if you get a number that ends in 0.5, you need to double all your values. And if you get a number ending in 0.3, you need to triple all your values. So I'll give you a second to jot this down, and then we're going to go through some examples, and then you're going to do some. So we're going to assume we have X number of grams, convert grams to moles using molar mass, divide all of those number of moles that we got in step 2 by the lowest, and then when we divide through, if we get a number ending in 0.5, that's where we're going to double all our values. If we get a number ending in 0.3, we're going to triple all our values. Otherwise, we'll just round up or round down. Okay, so if you're getting something that ends in 0.8, you just round up. If you get something that ends in 0.1, you just round down. But that 0.5 is like a half, right? So that's where we're going to double everybody. And the 0.3 would be like a third, so we're going to triple everybody. Right, so this is just a picture representation. We're going to convert grams to moles using molar mass. We're going to divide through by the smallest to get the mole ratio. That gives us our empirical formula. So let's go through this one together. What is the empirical formula of a compound that is 71.65% chlorine, 24.27% carbon, and 4.07% hydrogen? So I would have to give you these percentages, okay? That would have to be given to you. You have to have that data in order to do this. So the first thing you do is you're going to pretend it's a 100-gram sample, that just because that makes converting percentages to grams easy, right? If it's a 100-gram sample and it's 71.65% chlorine, that means that I've got 71.65 grams, right? So we just take all those percentages, drop the percent, substitute a gram, and now we're going to convert grams to moles using the molar mass, right? Now you don't normally get two values that are the same. This is just kind of a freak coincidence. And another thing that I want to advise is carry out extra decimal places here. Okay, don't round it to 2. Carry out extra digits, all right? Because that'll help you identify the smallest number more easily. Again, it's not normal to get two values to be exactly the same. That's just something that worked out in this problem. So you convert grams to moles. Now you look at those values. Which number is the smallest value? 0.021 is the smallest value. So I'm going to divide all of them by the smallest value. So 2.02 divided by itself is 1. 2.02 divided by itself is 1. 4.04 divided by 2.02 is 2. So notice none of these values end in 0.5 or 0.3. So I don't have to worry about doubling or tripling, right? Because these are all numbers that don't end in 0.3 or 0.5. So that last step doesn't apply here. So that means my final answer is CH2Cl. That's an empirical formula. I know it's an empirical formula because the ratio 1 to 2 to 1 does not reduce any further. CH2Cl is not a substance that exists. But in a few minutes, we will turn it into a molecular formula, which does exist. Does everyone see how we did this? Any questions on the process? Okay, you do this one. Para-amino-benzoic acid has the following composition: 61.31% carbon, 5.14% hydrogen, 10.21% nitrogen, 23.33% oxygen. And I want to know, what is the empirical formula? I will pause the recording while you take a stab at this one. All right, let's see the solution. So I had to give you the percent composition data, right? That have to be given. So anytime you see a big long list of percents, that should trigger in your mind, hey, this is the procedure I need to go through. All right, so the first thing I do is I convert grams to moles. Then I'm going to divide all those values by what? The lowest number, right? So I convert grams to moles, 5.105, 5.09. That's why I recommend carrying out extra decimal places so you could differentiate between ones like that. Although that one's not going to be the issue. Here's the smallest number. Do we agree on number of moles? Now we're going to divide through by the smallest. Again, none of these end in 0.5, so I don't have to worry about doubling everything. But just for pretend, okay, let's just pretend that this value came out to be 7.5. That's like 7.5, right? If this one, just for pretend, if it came out to be 7.5, I would multiply it by 2, but I would multiply all the other ones by 2 as well, okay? Because that's how you get rid of that 1/2. Again, let's just pretend. Let's pretend this came out to be 7.3. That's like 7 1/3, okay? How do I get rid of that fraction? I multiply it by 3, but I multiply everybody else by 3 as well. Otherwise, you don't have to worry about multiplying by anything, right? Because if it's round up or round down, you're good. So this gives us our final answer, C7H7NO2. Does the ratio 7 to 7 to 1 to 2 reduce any further? No. And that is a empirical formula of a substance that exists. If you know your organic, you can draw it now. And if not, you can wait till next semester. All right, now let's talk about a molecular formula. We already know that the difference between an empirical formula and a molecular formula is just multiplying by some number, right? Take an empirical formula, multiply it by 5. Take an empirical formula, multiply it by 8, okay? So what we need to do is we need to figure out what that number we're going to be multiplying by is. And so how do we get that? We get the molar mass of the molecular formula, which I would have to give you. Okay, I would give you the molar mass of the molecular. And then you would calculate the molar mass of the empirical formula. And then you just divide those two values by each other. M over E, molecular over empirical. Right? M over E. Spells the word me, so it's easy to remember. Molar mass of molecular divided by molar mass of empirical gives you the factor that you multiply by. And again, I would have to give you that molecular formula's molar mass. But you can calculate the molar mass of the empirical formula, because you'll have the empirical formula right in front of you. Is everybody cool on how to do this? So we're just dividing molar masses. That gives us the number that we then multiply by. Okay, so if you get 1.9, right, you round that to 2. So we just did this problem a few minutes ago, right? We came up with CH2Cl. Do you remember doing that a few minutes ago from the empirical formula percent data? So I said, okay, there's no such thing as CH2Cl. So let's find out the compound that really does exist. So there's the empirical formula. And I tell you, all right, the molecular formula's molar mass is 98.96. So what's the molecular formula? Well, we need to figure out what that factor is. Okay, so we take the molar mass of the molecular, which is given. Right, that was given in the problem. And then where did this 49.48 come from? Right, that's just the molar mass of the empirical formula. So 12.011 plus 2 times 1.008 plus 35.45. Okay, so you calculate the molar mass of the empirical formula. The molecular formula's molar mass is given. So when you divide those two values, you get a number that rounds to 2. So therefore, the empirical formula, you just multiply everything by 2. So you get C2H4Cl2. And that's a substance that does exist. Now that molecular formula is still a little ambiguous, because when we learn about organic chemistry, there are some isomers that exist. So you've got multiple structures that would have the same molecular formula. So you'd have to draw it out to get specific. But nonetheless, that's the molecular formula. Questions on how we do this? Easy enough, right? Okay, here's a 2-step problem. First, you're going to calculate the empirical formula. What is the empirical formula of a compound that is 30.45% nitrogen and 69.55% oxygen? So first of all, I just want you to calculate the empirical formula. Then, I'm telling you the molar mass of the molecular formula is about 92 grams per mole. So based on that information, what's the molecular formula? So you're calculating 2 things. You're calculating an empirical formula, and then you're going to turn it into a molecular formula. Excuse me. I'll pause the video while you work on that. Okay, so in the first part, we're going to calculate the empirical formula. And since there are only 2 percentages to deal with, it's not going to be a complicated calculation, right? And then we're going to take that empirical formula and use it to turn it into a molecular formula. So we're going to convert grams to moles. And then we're going to divide them both by the smallest, so the 2.173. So that gives me an empirical formula of NO2. Do we agree? And NO2 does exist, right? The ratio 1 to 2 doesn't reduce any further, so I know that I've got an empirical formula, not a molecular. Do we agree on the empirical formula calculation? We both get NO2? Yeah?
The only time triple is if it's like just 4 3, there's no additions out.
Yeah.
Okay, I got confused.
Mm-hmm. Yeah, that's why I always say carry out some extra decimal places. And so now we're going to take that empirical formula and we're going to figure out what our factor is. So the molar mass of the molecular was given in the problem. And then we have to calculate the molar mass of the empirical. So the empirical formula's molar mass is 46. The given was 92. So 92 divided by 46 is 2. So that means our molecular formula is N2O4. Pretty sure N2O4 was on the first test. That's one of the ones you had to name, wasn't it? It was either on the first exam or it was on the nomenclature proficiency, I think. It was on one of them. I remember seeing it. Do we agree? Okay. This one only does an empirical. I want to do a double step. So let's go to a different one. Here we go. This has got both in it. A compound with the molar mass of 142 grams per mole is 50.7% carbon, 9.9% hydrogen, and 39.4% nitrogen. What is its molecular formula? So I have to do both steps. The reason I skipped over the previous one is because it was only asking for empirical. I want you to take it all the way to molecular. Okay, last problem. So I didn't ask you, I'm not interested in even knowing what the empirical formula is here, right? I just said, what's the molecular formula? But you have to obviously calculate the empirical formula first as an intermediate step. So we have to first convert grams to moles. Then we divide through. Do we agree? Yes, yes, yes. So that's our empirical formula, C3H7N2. But the problem didn't ask about that at all. We are not even interested. So I've got to turn that into a molecular formula by getting a factor that we're multiplying by. So I came up with 2 as my multiplication factor. Did you? And then we're going to multiply through by that, C6H14N4. That would be my final answer. Do we agree? Do we agree? Do we agree? Final answer. All right, so that's where we're going to stop. So tomorrow is lab. Make sure you bring pre-labs and all that good stuff.